Hello, my name is Fawad Khan, and today I'm going to present a collaborative ontology development platform that provides different modes of operation and visualization methods. The aim of this platform is to bridge the gap between knowledge engineers and domain experts. Semantically coordinated semiconductor supply chains, short SC3, is an EU-funded project which addresses the creation of standardized ontologies for the semiconductor domain and related supply chains. In order to support this objective, we created a collaborative ontology development platform which uses user-centric approach to engage various stakeholders with different backgrounds. We define three user groups: experts, who are knowledge engineers providing the necessary know-how for ontology modeling. The intermediate group is to people with prior experience of ontology modeling, and the novice group addresses the users without prior experience with ontology modeling. Each user group has different requirements, therefore, we provide different modes of operation for individual user group. Additionally, we provide customization options for visual representations to reflect the previous experience of different users with different visualization methods. The ontology is the central point for all user groups. The different modes of operation provide specific functionalities for the different user group. On the right, we see modeling and editing operations. For example, an expert can use text-based modeling, an intermediate user can use a widget-based approach similar to Protege. A user without prior experience can use a visual modeling approach and create elements of the ontology directly in the graphical representations. On the left side, we see the visualization and communication as different modes of operations is designed for the individual user group. Ontologies are typically distributed as text files with different serializations. We need a model that serves as a foundation for all modes of operation. We are currently working on so-called resource relation model. This model is a textual representation of the ontology that is created through a pre-processing step in order to account for different serialization formats. It provides some reorganization of triple statements to enable different modes of operation. This model shall provide mappings and also inverse mappings to elements from the ontology. This model should serve as a foundation for all modes of operation. Here we see a short overview of the process for the creation of resource relation model. The data source in this case is an ontology. Data access handler fetches the ontology and processes it into a JSON format. The parser component then converts the JSON format into resource relation model. Resources provide the classification of triples into annotations, axioms, and types, and relation extend resources by providing additionally domain and range restrictions. We provide four modes of operation: a text-based mode, allowing user to inspect and edit the textual representation of ontology; a graph-based mode, which allows to see and edit the graphical representation of the ontology; a widget-based mode, allowing to interact with the ontology using forms and widgets similar to Protege; and a hybrid mode, which combines the three modes of operation in one user interface. In the following, we present features and functionalities of our approach. The current implementation of the approach uses different services, for example, storing the ontologies or processing them in order to create resource relation model. Here we see an index of all the ontologies currently uploaded to the platform, its names, and also a short description. Here we also provide an upload functionality to upload new ontologies from textual format, for example TTL file. The names and descriptions of the ontologies are parsed from the text file, which can be edited and changed during the upload process. The upload process also incorporates a validation mechanism which needs to be further enhanced for advanced validation. Once we choose a particular ontology from the index list, it takes us into hybrid modes of representation of that particular ontology. On top, we see the navigation bar of the web application. It provides functionality for ontology selection and user login. Here we see the functionalities for selecting different modes of operation. Currently, we have selected the hybrid mode as a default mode. In the hybrid mode, we provide collapsible sidebars that provide meta information of the ontologies. In the center, we see the main widget displaying on the left the resources and on the right the relations stored in the resource relation model. Each card represents a resource or a relation. In the hybrid mode, cards provide a header and additional collapsible elements to display the body, the graphical visualization, or the widget based representation. The header reflects a type assertion of the resource. The body reflects annotations and axioms in the turtle serialization format. The graph visualization displays all edges and elements of a particular resource. The widget-based representation provides a protege like forms and widgets. Here we provide functionality for adding and deleting annotations and domains and ranges. In the hybrid approach, we provide additional filtering and search mechanism. The filtering mechanism can be used to display elements of ontology that share the same prefix. The search mechanism provides an autocomplete functionality and highlights elements that match the search term. The next mode of operation is a textual representation of the ontology data. Using our resource relation model and partially implemented inverse mapping, we can reconstruct the turtle serialization for the displayed ontology. In the graph-based mode, we provide visualization of the ontology using node link diagram. The collapse and expand feature allow the user to control the information flow. Additionally, we provide different visual notations for displaying the ontology graph. Currently, we support vowel notation and the UML notation. In the UML-based representation, we apply nesting operations for data type properties and their asserted data types, for example, RDFS literals. Furthermore, we provide customization options for individual nodes in the ontology graph. Currently, we support only a limited set of customization options such as color, font size, and increasing the margin between the text label and the rendering shape. In summary, we already provide prototype implementation for different features for the ontology graph visualization. We provide two different visual notations, vowel and UML notation. We provide interaction with the ontology graph via collapse and expand mechanism to control the amount of information and thus reduce the cognitive load of the individual task. And we also provide customization for the individual nodes to highlight specific information. In our next step, our focus is on enhancing the functionality of viewing ontology data from different perspectives. The next step will include the modeling and editing functionality for different modes of operation and synchronization between different modes using resource relation model as foundation. Furthermore, we plan to extend the customization feature to full range provided by Gizmo customization options. We also plan to provide single sign-on solution for authentication and authorization. On this slide, we would like to provide contact information, the current prototype URL, and the project source location on GitLab. With this, I would like to thank you for your attention.